In this section, we're going to be talking about how to find the intervals in which a function is increasing or decreasing, and we're going to be talking about how to find relative extrema of a function using the first derivative test. So before we get started with how to find it, let's talk about what increasing and decreasing means mathematically. So a function f is increasing on an interval when for any two numbers x of 1 and x of 2 in the interval, if x of 1 is less than x of 2, then f of x of 1 is less than f of x of 2. So as x increases, y is also increasing. A function is decreasing on an interval when for any two numbers x1 and x2, if x of 1 is less than x of 2, this implies that f of x of 1 is greater than f of x of 2. So as x is increasing, y is decreasing. So as x moves to the right, if the graph moves up, then f is increasing. And if the graph moves down, then y is decreasing. So as you can probably guess, this is heavily related to slope of a function. So basically, wherever you have a negative slope, you're going to be decreasing. Wherever you have a positive slope, you're going to be increasing. And wherever you have a slope of 0, you're going to be constant. So remember that the derivative is also related to slope. So wherever the derivative of x is less than 0, you're going to be decreasing. And wherever it's greater than 0, you're going to be increasing. And another thing that's important to note is that critical numbers are what are going to form the boundary between increasing and decreasing intervals. So basically what we're going to do is we're going to form some intervals that are bounded by those critical numbers, and then we're going to test for increasing and decreasing functions using the derivative. So if we let f be a function that's continuous on a closed interval and indifferentiable in an open interval, if f prime of x is greater than 0 for all x in that interval, then f is increasing. If f prime of x is less than 0 for all x in that interval, then f is decreasing. And if f prime of x is equal to 0 for all x in that interval, then f is constant. So we're going to be using that to figure out where our function is increasing and decreasing. So for this example, I'm going to start by my step 1. I'm going to find my critical numbers because those are my boundary points. So for step 1, I will find the derivative, f prime of x, which is 2x minus 2. That exists everywhere, and it's equal to 0 where x is equal to 1. So x equals 1 is my critical number. Step 2, I'm going to set up my intervals. Now I'm going to actually do this in a chart off to the side so you can see what it looks like. So I'm going to pick intervals, and the boundary point for my intervals is going to be at 1. So that means that I have two intervals because the domain of this thing is all real numbers. So the division happens at 1. And for step 3, I'm going to choose a test point in each interval. Now, when you pick a test point, you only have to actually evaluate at the test point because it's kind of like checking the temperature of a cup of coffee or checking the chlorine in a pool. You don't have to check every single drop of liquid, you just have to check a single drop of liquid in order to get a picture of what's happening on the whole pool. So we're going to do that here. We're going to pick 1 point in each interval. And the nice thing about this is you get to pick your points, so you can use whatever is the most convenient. Even if you have some kind of nasty boundary like the square root of 7, you could pick 0 and 10 on either side of it just because they're easy to plug in. So for this first interval, I'm going to use 0, and the second interval, I'm going to choose 2. And then step 4, we want to evaluate f prime of x at each test point. So I'm going to plug these into f prime of x. So f prime of 0 would be 2 times 0 minus 2, which is negative 2. And 2 would be 2 times 2 minus 2, which is going to be 2. So this one's negative and this one's positive. So step 5, we want to make our conclusion, and that's going to use the test. So for step 5, my conclusion, because f prime of x is negative on this interval, we can say that it's decreasing. And because f prime of x is greater than 0 on this interval, we'll say that it's increasing. So f is decreasing on the interval from negative infinity to 1, and it's increasing on the interval from 1 to infinity, and that would be my answer. And you can see here, this is the graph of the function. You can definitely see where it's decreasing from negative infinity to 1 and increasing from 1 to infinity. So you can always check these by glancing at a graph. So this is basically the steps of what we did. We set up our open intervals, we found our critical numbers, we set up the intervals, we determined the sign of f prime of x on one test value, and then we used the theorem 3.5 to determine what we were doing. So this is what we're looking at. And you can absolutely, have intervals that go from negative infinity to infinity and such and such, so forth. And if there are no critical numbers, it may be that you're actually increasing on the whole interval or decreasing on the whole interval. So let's do another example. I want to find the intervals on which f of x equals x times the square root of 16 minus x squared is increasing or decreasing. So for step 1, we're going to find our critical numbers. So I'm going to find f prime of x. And to do this, I need to use the product rule. So f will be equal to x, and g will be the square root of 16 minus x squared. And it turns out I'm actually going to have to use the chain rule in this as well. So f prime is easy. That's just going to be 1. G prime is going to be 1/2 times 16 minus x squared to the negative 1/2 times the derivative of the inside, which is negative 2x. And all that simplifies to be x over the square root of 16 minus x squared. So f prime of x is fg prime plus gf prime, which is going to be x times, and actually this should have been negative, times negative x over the square root of 16 minus x squared plus the square root of 16 minus x squared times 1. And I'm going to find a common denominator, so I'm going to multiply this by the square root of 16 minus x squared over the square root of 16 minus x squared. So that gives me negative x squared plus 16 minus x squared divided by the square root of 16 minus x squared, or negative 2x squared plus 16 divided by the square root of 16 minus x squared. Okay, so all that just to find the derivative. And the reason why I need the derivative is because I need to know where it doesn't exist and where it is equal to 0. So before we get started, I do want to just make a note of the domain of my function. So the domain here, I know that anything I plug into that square root has to be greater than or equal to 0. So that tells me that x squared has to be less than or equal to 16. So x is going to have to be between negative 4 and 4. So anything that we get as a critical number that's outside of that, that interval from negative 4 to 4, we can actually rule out. So f prime of x does not exist where the denominator is equal to 0, where 16 minus x squared equals 0, so that's x equals plus or minus 4. Those are our boundary points anyway. F prime of x equals 0, where negative 2x squared plus 16 equals 0, or 2x squared equals 16, so x squared equals 8, and x would be plus or minus the square root of 8, or plus or minus 2 root 2. So when we set up our intervals here, remember we're only looking at the domain being carved up into subintervals. So our domain goes from negative 4 to 4 anyway. So I'm going to create intervals from negative 4 to negative 2 square root of 2, from negative 2 square root of 2 to 2 square root of 2, and from 2 square root of 2 to 4. And actually, because those happen to be critical numbers also, we're going to use parentheses there. So I've got 3 intervals, and I want to pick my test points. Now this is a classic example of where you can be smart about choosing your test points. So when I look at this, 2 square root of 2, or the square root of 8, is about 2.8, so we've got negative 2.8 and 2.8. I'm going to choose wisely. I'm going to work smarter, not harder, so I'm going to plug in a negative 3 here so I don't have to deal with any fractions. Here I'm going to plug in a 0, and here I'm going to plug in a 3, because 3 is between 2 square root of 2 and 4. Got a little stray comma there. Okay, so I'm plugging these into f prime of x. Remember, that's this equation right here. So I'm going to just do that on my calculator. So I'll have negative 2 times negative 3 squared plus 16 divided by the square root of 16 minus that squared. And I don't even really care about the exact value of it. I just want to know if it's negative or positive. I get about negative 0.76, which is definitely negative. When I plug a 0 in, to that I would get 4, which is positive. And when I plug a 3 in, I get that negative 0.76 again. Again, one of the only times I'm going to tell you I don't care what the exact answer is, I just want to know if it's negative or positive. So my conclusion then is that we are decreasing on this interval, we are increasing on this interval, and we are decreasing on this interval. So my answer is going to be that f is decreasing on the interval from negative 4 to negative 2 square root of 2 and 2 square root of 2 to 4. F is increasing from negative 2 square root of 2 to 2 square root of 2. So that would be my answer. So looking at another one of these, I'm going to find my critical numbers. So I'm going to find the derivative f prime of x is going to be 6x squared minus 6, and I'm going to set that equal to 0. So I get 6x squared equals 6, x squared is 1, so x would be plus or minus 1. I have no potential domain problems here, nothing that could be causing any issues, so my intervals that I set up, there's going to be 3 of them. We're going to go from negative infinity to negative 1, from negative 1 to 1, and from 1 to infinity. My test points, I could pick negative 2, 0, and 2. Again, it's just up to you what you want. I'm going to plug these into f prime of x, so this will be 6 times negative 2 squared minus 6, which is 24 minus 6. Again, I don't even care what the answer is, I just care that it's positive. 6 times 0 squared minus 6 is going to give me negative 6, which is negative. And 6 times 2 squared minus 6, again, is going to be positive. So our conclusion is that we are increasing, we are decreasing, and we are increasing. Now you do want to be careful with this. Don't assume that because you're going from one interval to the next that it's going to necessarily change. There are some examples where, or some cases where maybe your intervals are actually formed by an asymptote or something along those lines, or you may just have a place where it happens to have a 0 derivative, and it's highly possible that you could have 2 increasing intervals next to each other. So don't assume it's going to alternate. You do have to check all 3. But here we would be increasing on the interval from negative infinity to negative 1, and from 1 to infinity, and we'd be decreasing on the interval from -1 to 1. So that would be my answer there. So there are some special functions which are always increasing or always decreasing, and those are what are known as strictly monotonic functions. So strictly monotonic functions are either increasing or decreasing on the entire interval. So for example, this one right here, f of x equals x cubed, would be strictly monotonic because it's increasing on the whole interval. It never stops increasing. It might increase slightly slower on some portions of it, but it's still increasing. This one has a constant section in the middle. It's actually defined as a piecewise function, and this is monotonic, but it's not strictly monotonic. It's just non-decreasing on the entire interval. So those are some situations that you want to be aware of as well. And an important thing to note right here is if you did find the derivative of x cubed, you would get 3x squared, which would have a critical number at 0. And if you try to set up your intervals, you'd see that it was increasing on both sides of it. So remember, critical numbers are the candidates for places where it changes, but it doesn't necessarily mean that it has to change at that point.